Hello friends, welcome back. Before we start off with the questions, there is one small thing I need to mention. In the previous video, I missed out this part. Well, this formula, alpha 1, where alpha 1 was the exponent for any prime number in the expansion of, it's not n here, it is n factorial. Okay, so please note this change. If n factorial is written in this format, if n factorial is written as p1 in p1 for alpha 1 into p2 for alpha 2, where p1, p2, etc. are its prime divisors, then alpha 1 is given by n by p1. Okay. There is no change in the formula. The formula is absolutely correct, where the square bracket is nothing but the greatest of the function. But this is for n factorial. Okay. So if it is 25 factorial, the exponent of say 5, that will be given by 25 by 5, that is 5, plus 25 by 5 square is 1. The greatest integer functions of those things. So we get that 5 or 6 is what we will get. Okay. Right. So now moving on to the question. The first question is, find the coefficient of x power 24 in x square plus 3 by 3a by x power 15. Okay. For this kind of question, first of all we write down the term. Say r plus 1 term is written as 15 c r x squared power 15 minus r into 3a by x r, right? This is equal to 15 cr x power 2 into 15 minus r is 30 minus 2r into 3a power r by x power minus r. X power divided by x power r or multiplied by x power minus r. Right? So writing this as, in terms of x, we get x power 30 minus 3r, right? Minus 2r divided by x power r is still minus r only, so x power 30 minus 3r. Now, we need the coefficient x power 24, right? So, our 24 should be in place of 30 minus r. Well, that gives us 30 minus 3r is nothing but 24, right? So, we just have a simple equation in this and we get our r to be equal to 2. Now, once we know what our r is, we can write the coefficient. The coefficient is this part. We don't need the binomial coefficient, we need the whole coefficient. So, which is equal to 15c to 3a squared. Right, so it's pretty simple. You can calculate this. 3a is squared is 9c squared, 9a squared into 15 into 14 by 2, that is 105. So you have 945 a squared. This is the coefficient of x power 24. Okay. Next one, find the coefficient of x cube in the expansion of 1 plus x plus 2x squared into 2x squared minus 1 by 3x power n. Let us start with the term of the any general term of the next expression. This one. So let us write er plus 1. Er plus 1 is 9 cr 2x squared power 9 minus r into minus 1 by 3x. Don't forget to write minus here. It's minus 1 by 3x into r. So that gives us 9cr into 2 power 9 minus r minus 1 by 3. Let's write all these coefficients earlier and then let's pull up the coefficient of x. So it's 2 into 9 minus r, that is 18 minus 2r, and again divided by x power r, right? So minus r. So what we get in the end is 9cr 2 power 9 minus r minus 1 by 3 power r into x power 18 minus 3r. Well, so analyzing this term, we see that x is always the coefficient of x is always a multiple of 3, right? 18 minus 3r. Whatever value r can take here, it will always be a multiple of 3. 13 minus 18 minus 0 is 18, 18 minus 3 is 15, 18 minus 6 is 12, so all multiples of 3. Well, that means from this side, for the question of x cube, what we needed from this side is something which should also be a multiple of of an exponent 3, right? So that both of them multiply to give it x cube. But we see that we have x and x squared, which will never give when multiplied with some other x power 3n as x cube. So we see that it should only be the first term which should be multiplied, and hence now this part should correspond to x cube, right? So x power 18 minus 3r is x cube. That means 18 minus 3r is equal to 3, or r is equal to 5. So once we now know r, we can write the coefficient. Coefficient is 9c5, 2 power 9 minus 5, that is 2 power 4, and you have minus 1 by minus 1 power 5, that is minus 1 actually, by 3 power 5. It's minus 1 by 3 power 5. Solving this whole thing, we get coefficient as minus 224. So the coefficient is actually a negative one. It's minus 224 by 7. This is the coefficient. Okay. So writing this, so आगे सुपर बोला बात कर. So writing solving this, we get the coefficient is minus 224 by 7. Third question: if the coefficient of second, third, and fourth terms in the expansion of 1 plus x power 2n are in AP, then show that 2n square minus 9n plus 7 is equal to 0. Okay. Now, note that in these kind of questions, you have to be specific how you write the binomial expansion. If there is 1 plus x power 2n, 1 plus x power 2n, will always write the r plus 1 term in this way. Because it has been given which specific terms are in AP, right? So, just reversing the order and reversing the order of the expansion will never give you the same result. So this is 2n c r 1 power 2n minus r. Okay? So this is not x power 2n minus r. Though it's the same thing, the series is still the same, but the terms will not be the same. The x power r. This is actually 2n c r into x power r. So this is the rth term of this expansion. Now the second term will be that means r is equal to 1. So 2n c1 x power 1. Okay, let's just forget the x terms because only the coefficient is important. 2n c1. The next one is 2n c2. And the fourth term is 2n c3, right? You see that there is no other contribution from anything else. So it's just the binomial coefficients which are in AP, right? So let us solve all of them, and we know that twice the arithmetic mean or the second term will be equal to the sum of the first and third terms. So 2 into 2n c2 is equal to 2n c1 plus 2n c3, right? So that gives us 2 into 2n minus 1 by 2 is equal to 2n plus 2n into 2n minus 1 2n minus 2 by 3 into this is 3 into 2, that is 6. Now we see that 2n can always be cancelled. This common factor in everything. Here the 2 will get cancelled. So it is 2n minus 1 equal to 1 plus 2n minus 1 into 2n minus 2 by 6. Right? So, expanding this, we get 4n square minus 3 into 2n, right? 6n plus 2, that into 6 times 2 minus 2n, that is equal to 0, or 4n square minus 6n, sorry, plus 6 times, right? So it is minus 12n plus 12 plus 12 is 14. So this is 4n square minus 18n plus 14 is equal to 0. Dividing 4 by 2, we get 2n square minus 9n plus 7 is equal to, right? So this is what we're supposed to show. So we just expand the terms, we take their coefficients and apply the condition of arithmetic progression and we arrive at the result. Find the term which does not contain irrational expression in the expansion of fifth root of 3 and 7th root of 2 whole power 24. Okay. So again what we do is we write the rth term and try to analyze that. Okay. So again PR plus 1 is 24 CR. Now fifth root of 3 is nothing but 3 power 1 by 5, right? So it is 3 power. This term will be now 24 minus R by 5. The next term is 2 power 1 by 7, right? That power R, so that is R by 7. Okay. Now, it says the term does not contain irrational expression. That means both of them should be just integers, right? That means 24 minus R by 5 must be an integer. So let us call this as M, where M is an integer. Similarly, R by 7 is another integer. Now, it may or may not be M, right? So we take it as M, where both M and N are integers. Okay. So now, we know that R can take the values from 0 to 24, right? But moreover, from the second equation, we see that R is 7 times an integer, and since R can take values from 0 to 24, the only values R can now take are 0, 7, 14 and 21, right? So only these 4 values. Substituting them in the first equation, we see that 24 minus 0 by 5 will not give an integer, minus 7 by 5 will not give an integer, 24 minus 14 by 5 is 10 by 5, that is 2, that is an integer, right? So R is equal to 14, and then let us take 21. 24 minus 21 is 3 by 5, again not an integer. So only R equal to 14 can give us a term which does not contain an irrational expression. Okay, so we'll now show the value of R equal to 14, and let us see what we get as the term. Okay, so term is 24 C 14 3 power 24 minus 14 by 5, right? 3 squared, and 2 power 24 14 by 7, that is again 2 squared. This is 24 C 14 3 squared into 2 squared, or 6 squared, that is 36. Right? So this is our term, and as you can clearly see, 24 C 14 is an integer, and into 36, which is another integer, must be an integer. So there is no irrationality. Okay. Now, fifth one. Given that fourth term in the expansion of 2 plus 3x by 8 whole power 10 has the maximum numerical value, find the range of values of x for which this will be true. Okay. Now, first of all, we have always seen that in a binomial expansion, the terms will always increase and then decrease, right? or it will be the other way, it will decrease and then increase. So from this we know that if the fourth term has the maximum numerical value, then it must be greater than the third numerical value, which in turn is greater than the second numerical value, right? So from the left hand side we just need to prove that fourth term should be greater than the third term, right? And similarly the fourth is also greater than the fifth term, and fifth will be further greater than the sixth term, right? So again we just need to prove that fourth is also greater than the fifth term, right? So for finding this range, what we will do is we will just compare the fourth term with the third term and the fourth term with the fifth term, and see where x lies. Okay, so D4 by D3, and moreover we will put a mod here, right? Because what we need is just the coefficient with the positive sign. So it's just the mod which is required for this analysis. So D4 by D3 must be greater than 1 or greater than or equal to rather, and similarly D4 by D5 again greater than or equal to 1. Now let us write any r term. So r plus 1 term is 10CR 2 power 10 minus r 3x by 8 power r, right? So we have 10CR 2 power 10 minus r 3 power r by 8 power r, right? We just keep it at this. You'll see the reason why. There is no need to actually. You can write 8 again as 2 power 4, right? So 8 power r becomes 2 power 4r. Then you have another term in 2. So we can probably add their or subtract their exponents and simplify this further. You'll see that that is not that necessary here. Okay, so now let us look at the first equation, D4 by D3. So our r is 3 and 2. Right, so for the first one it is 3, the second one is 2. So the first expression will give us 10C3. We then have 2 power 10 minus r. So this 2 power 10 minus 3, 7. 3 power 3 by 8 power 3. Right? This divided by 10C2, 2 power 6, 3 power 4. Sorry, this is 8, right? Actually, this is 2. 3 squared by 8 squared. The mod of this, okay. Actually, in this question, x also needs to be taken as the coefficient. We will be considering the whole term, right? The whole term has some numerical value. When we have some value of x, say x is equal to 1, right? So that is why we will not ignore x here. We will also write x, right? So this now is greater than or equal to 1. First we will just simplify this. Now you can see that actually this 2 power 7, right? That cancels with all the exponents except 1. So I just remove the exponent here. Similarly, 3 squared x squared by 8 squared, this whole thing will just remove and cancel all the exponents. And so this is the reason why simplification of the whole term was not necessary, because what you get in the end is just this much. Okay, so 10C3 actually is 10 into 9 into 8 by 6, and 10C2 is 10 into 9 by 2. Again 10 9 cancel. 2 cancels with 3 here. What you have is just 8 by 3, and what you have from the numerical part was 3x by 8 divided by 2, right? So this is greater than or equal to 1 actually. So again 8 by 3 here, and we have 3x by 8. So this 8 by 3 cancels with 3 by 8, and you have just x by 2 is greater than or equal to 1. That means mod of x is greater than or equal to 2. Right? So you have found one condition. Let's look at the second one. The second one is 10C. Now that is again 10C. The same thing as the first one, but denominator will be different now, right? So you have 10C3 2 power 7 3x by 8 cube that divided by 10C4 2 power 6 3x by 8 power 4, right? So for the binomial coefficients, that is 10 into 9 into 8 by 6 divided by 10, 9, 8, 7 by 6 into 4, right? That's 24 actually. So 10, 9 and 8 cancel. 6 cancels with 6 here. You have 4 left. And here, you see that 2 power 6 cancels. You have only 2 here. And this whole 3x by 8 cube cancels and you have only 3x by 8 in the denominator. So that is 2 by 3x by 8. So which I can take to the numerator. Okay. So from the binomial side we have only 7 by 4, right? So you have 7 again goes to the numerator. 4 into 2 into 8, that is 64. In the denominator you have 7 into 3, that is 21 into x is greater than equal to 1. Or mod of x is actually less than equal to 64 by 21. Right? So this gives us our second condition. So we know that x is actually greater than 2, whereas x is less than 64 by 21. Again, the modulus only. Right? So it's not just x, also the negative of x. Now 64 by 21 is actually greater than 2. So this kind of possibility exists. So we know that x belongs to minus 64 by 21 to minus 2. That union 2 comma 64 by 21. So this is the total range of x for which, so the original question was the fourth term should be maximum, right? That should have the maximum numerical value. So we get this as the condition in which that will be correct. Okay. Sixth one, prove that C0 CR plus C1 C for CR plus 1 plus C2 CR plus 2 all the way till Cn minus R into CR is 2n factorial by n minus R factorial into n plus R factorial. Okay. Now for this kind of question, what we do is, again C0 is understood to be NC0. Okay. So it's by default n which will be in the superscript. Okay. Now you see that that the binomial coefficients actually change in a very set pattern, right? The first one actually increases by 1. And similarly, it does the second part, CR, CR plus 1, CR plus 2. Okay. So what we do is, we first write 1 plus x power n. Okay. Now what is this? C0 plus C1x C2x squared. Excuse me. Okay. So all this way, the CR x power r. Right? Again, it will go on. We don't know where it ends, right? We don't know the value of n. Now we actually reverse this and write. So inside we just reverse it and we write this as x plus 1 power n. So that gives us C0 power C0 x power n, C1 x power n minus 1, C2 x power n minus 2, CR x power n minus r, right? Okay, so now what we do is, we multiply both of them. Okay, so on the left hand side, I'll take the whole expression here on the right hand side to the on the left hand side. Okay, so that is C0 plus C1x plus C2x squared, like this, right? Plus CR x bar r, some general term. This multiplied by C0 x bar n, C1 x bar n minus 1, C2 x squared, CR x bar n minus r, all the way. Okay, now on the right hand side, if you look, we actually have written the same expression twice, right? So this is nothing but 1 plus x power 2n, right? Okay. So now what we do is, if you look at the result of the proof, on the right hand side we have 2n factorial by n minus r factorial into n plus r factorial. Okay, so this is nothing but 2n cr, c n minus r, right? If you look carefully, this is nothing but 2n c n minus r, right? So this is nothing but the n minus r plus 1 term of this expression, right? So what we do is, we just compare the coefficients of x power n minus r. So we just compare the coefficients of x power n minus r. So why I do is x power n minus r. Actually, you can argue that we could have taken x power n plus r, right? Because both of them will give the same binomial coefficient because of the symmetry. However, I do that because if you look at the left hand side now, what we required was C0 to C bar r, so C0 to CR, right? So I have C0 here, I have CR. That is nothing but x power n minus r. And so my case is solved here. My confusion is over. I should take x power n minus r. I mean, that is just because of my expansion here. I can obviously take C0 to CR also from this one, but then this could be confusing for you sometimes. So if I write it in the reverse way, these two expressions, so writing the second expansion first, then again that will be easier for you, right? C0 into CR. Okay. So now we just compare the coefficients of x power n minus r, and what we get here is C0 into CR plus C1 into, now again the next term here will be one lesser, right? Okay, just a second. This is not x squared, this is x power n minus 2, right? So these are decreasing actually. So if I go to the next one, then that will give me x power n minus r, right? This is C1 into r plus 1. Similarly C2 into r plus 2. Like this. Till Cn minus r Cr. That will give me 2n C n minus r, right? So I just expand that r plus 1 C2 r plus 2 all the way Cn minus r actually Cr, that will give me 2n factorial by n minus r factorial n plus r factorial. So the result has been proven now. Next question. If 1 plus x bar n is written as sigma ncr x bar r, prove that mcr nc0 plus mcr minus 1 nc1 plus mcr minus 2 nc2 all the way till nc0 is equal ncr is equal to m plus n cr. So again we see that this somehow is related to the binomial coefficients. The binomial coefficients are again related to the exponents of r, exponents of x, right? So what we do is we first write 1 plus x bar n, that is given here, nothing but C0 C0 x bar 0 plus C1x C2x squared like this. So CR x bar R, right? Now we consider 1 plus x bar m, okay? And we write that in the same way. I'll just write in here so that you don't get confused here. Yes, sorry. We have MC0, MC1 x, MC2 x squared, MCR x bar R. Okay. Now what I do is, again I multiply both of them. I just swap the sides. Right? Just multiply with the second expression. Well, that gives us 1 plus x bar. Now you see that both of them have the same expression, right? Only the exponents change. So the exponents get added up and plus it. Okay. Now what I do is, I just compare the coefficients of x bar R here. Okay. So comparing the coefficients of x bar R, what I see is, now x bar R is here for the first term, right? So this is MC0 into MCR, right? So that is what we get in the result, right? So we are actually proceeding in the correct way. Now you see that for the first expression, actually for both the expressions, the exponent of x, okay, the exponent of x actually increases in the right side, right? So if you have to maintain the coefficient of any term, what you need to do is, you have to move one from the left hand side while moving left, moving right for one expression, and moving in the opposite direction for the next one, right? So we get MC0 and MCR plus, if it is MC1, because we can only move left now, right? This must be MCR minus 1. Okay. MC2, MCR minus 2, all the way till NCR, MC0. Right? This must be equal to the quotient of x bar R in 1 plus x bar m for n plus n, which is pretty obvious. It must be n plus NCR. Okay, so we see that our result has been proven. Right? Okay. Now, if 1 plus x bar n is equal to again CR x bar R, show that C0 by 2 plus C1 by 3 plus C2 by 4 all the way till Cn by n plus 2 is equal to n into 2 power n plus 1 plus 1 by, okay, so the result has been given. Obviously we need to start from the left hand side, because proving it from the right hand side will just be almost impossible, right? Unless we know the proof from the left hand side. Now, say this is nothing but, suppose the sum, this, I represent the whole sum by S. And say these are the different terms in it. Okay, so the overall n plus 1 terms. And so I write the rth term. The rth term can now be written as NCR minus 1 by R plus 1. Right? You can just take it for use. The first term is given as C 1 minus 0, that is C0 by 1 plus 1. So C0 by 2, that first term is correct. Then you have C1 by 2 plus 1, that is 3. Right? The next term is C3 minus 1 by 3 plus 1. Okay. So let us just expand this. Now what I do is, I'll use a very important property which was covered in the previous video. The property said NCR by R plus 1 is equal to n plus 1 CR plus 1 by N plus 1. And if you remember, it was NCR by R plus 1 is equal to N plus 1 CR plus 1 by N plus 1. Okay, obviously these must be the next constant N plus 1 R plus 1, and here you have R plus 1 and N plus 1. This is the property we will be using here. But if you remember, I'd also caution that be careful about these things. There must be R here and R plus 1. They must be different. They must be successive, and that too increasing by 1. Okay, but here you have R minus 1 and R plus 1. Right? There is a difference here, a difference of 2 here. So we just bridge that, and how we do that is we multiply and divide by R. Alright. Now I have it in this format, right? So I write it this that way. So this is NCR and this. This into NC. So this will be N plus 1 now. The R minus 1 also increases to 1, so that is R. And this becomes N plus 1. Right? So I have R by R plus 1 into N plus 1 CR. That can now be written as 1 by N plus 1. What I do is I write R by R plus 1 as R plus 1 minus 1 by R plus 1. Right? So I have R plus 1 minus 1 by R plus 1. Right? The numerator is still R. This into N plus 1 CR. Right? This is 1 by N plus 1 into. Now this is nothing but the first term is just 1. Right? If you just take this, we have N plus 1 CR minus N plus 1 CR by R plus 1. Right? So this was the purpose for me doing it this way. You can now see that the second term is again of this form, NCR by R plus 1. Right? So this is 1 by N plus 1. N plus 1 CR minus, this is nothing but N plus 2 CR plus 1 by N plus 2. Okay. This is our TR. Right? Now that we have obtained it in this format, the sum is very simple thing. So the sum can now be written as. If you remember, there are N plus 1 terms here, right? So R actually varies from 1 to N plus 1 of this thing. N plus 1 CR, the whole thing divided by N plus 1. I'll write this later. R plus 1 by N plus 2 and multiplied by 1 by N plus 1. Okay. Now the only thing left here is just expansion of this whole thing. So I just take the first terms. Okay. The first terms are nothing but N plus 1 CR from 1 to N plus 1. So be careful, there is no 0 here. There is C1, N plus 1 C2, N plus 1 C3, all the way till N plus 1 C, N plus 1. Right? So this is the first term. The next is 1 by N plus 2 into. Now we have N plus 2 C R plus 1. Right? So the first term is actually N plus 2 C 2, and then we have N plus 2 C 3. Again, with N plus 2 C N plus 2. Right? Now this is well known, right? The first one is actually, if there was N plus 1 C0, we could have written that as 2 power N plus 1. But since that is not present there, we just write this as 2 power n plus 1 minus 1. Okay. Similarly, the second one has 2 terms missing. So instead of 2 power n plus 2, this is 2 power n plus 2 minus n plus 2 c1, which is nothing but n plus 2, right? Minus 1. Right? So what we have here is, again I just multiply n plus 2 here, take that common. So n plus 2, 2 power n plus 1 minus n plus 2, that is minus of 2 power n plus 2 plus minus becomes plus, right? Plus 1. These terms cancel. And for this one, okay, you see that 2 into 2 power n plus 1 will give you 2 power n plus 2, right? So this term also cancels with this one, this 2. So what you have left here is n into 2 power n plus 1 plus 1 by n plus 1 into n plus 2. Okay. So we have proven that our expression is equal to n into 2 power n plus 1 plus 1 by n plus 1 into n plus 2. This question is pretty straightforward. Question says find the remainder when 7 power 1 by 3 is divided by 25. Okay, just see how this kind of question is done. What we do is we just express 7 power 103 in terms of a binomial expression. The 7 can the power 103 can be written as 7 into 7 power 102. Now 7 power 102 can be written as 7 power 2 into 51. Right? That is 7 into, now 7 squared can be written as 49. But 49 is about 50 minus 1, right? So this 50 minus 1 into 51. Right? Now why I write it in this form will be pretty clear once I write the next step. So expanding this is nothing but, right, 7 times the whole summation, which is 51 CR 50 power 51 minus R minus 1 power R. Right? This is my whole term here. So every term is actually given by 7 times of 51 CR 50 power 51 minus R minus 1 power R. Right? So you see that every term contains 50. Since every term contains the factor 50, it must be divisible by 25, right? Except the term which will not contain the term 50. Now, which term will not contain the term 50 here? Let us look at whenever 50, now the exponent 51 minus R becomes 0, this will not contain 50, right? So we have that term will be equal to that specific term, that dr plus 1 will be equal to R is equal to 51, right? So the 52nd term, that is equal to 7 or 51 C51, that is equal to 1. Right? 50 power 0, that is 1, minus 1 for 51, that is minus 1. Right? So this is nothing but minus 7. Right? So we see that in this expansion, all the terms can be written as a multiple of 50 and hence a multiple of 25. Right? Except the last term, which is nothing but minus 7. Right? But you cannot have a negative number as a remainder, right? So you can just, out of the remaining part, which is a multiple of 25, you can just take a 25 from that and you have the remainder as 25 minus 7. You can just add 25 to it and you have the remainder as 18. Okay. So this is how we solve this kind of question. We just expand 7 power 1 in a specific way so that you can express the expansion in terms of 25, right? So we see that we use the fact that 50 is a multiple of 25, and hence finally we get the remainder as 18. Right. I is the integral part and f is the fraction part of 2 plus 3 power n. Then prove that I plus f into 1 minus f is equal to 1. Note that the second factor has 1, not I. Also find out if I is order even. First of all, I can write down I plus f is equal to 2 plus 3 power n, right? Suppose 2 plus 3 power n is equal to, say, 555.732, right? This is just a assumption I have taken. This will definitely not be correct. Okay. So now 555 is an integral part, right? This is the integer. Whereas the fraction part is 0.732. So I plus f must be equal to 2 plus 3 power n. Now I see that 2 plus 3 power n into 2 minus 3 power n is equal to 4 minus, right? This is a plus b into a minus b. This is 4 minus 3 power n, and which is equal to 1. And so I observe this part. Also note that f must be equal to it cannot be 1, right? F cannot be 1. But it can always be 0. F can always take the value 0. Now that I have seen that 2 plus 3 into 2 minus 3 whole power n is equal to 1, what I do is I just assume 2 minus root 3 power n as f dash. Okay, this is just some different number f dash. Okay, now what is 2? What is root 3? Root 3 is something like 1.732, right? 1.732, and since it's a rational number, I will just write it this way, 1.732. So we know that 2 minus root 3 is definitely less than 1, but definitely greater than 0 also, right? Now, raising both sides to power n, I still have this inequality, right? So if there is any number which lies between 0 and 1, if you keep increasing its exponent, right, integral exponent, you will still have the value between 1 and 0, right? You can actually further narrow it down, but for just our sake, we'll just put it in this way, right? So 0, 2 minus root 3 power n will lie between 0 and 1, right? But we have 2 minus root 3 power n as f dash, right? So f dash also lies between 0 and 1. But there is strict inequality here. It's definitely greater than 0 and it's definitely lesser than 1. Now what we do is we just expand 2 plus 3 power n and add it to 2 minus root 3 power n. Right. So if you remember, all the in this kind of situation where you have the same exponent and the second term is just changes sign. So you have plus root 3 here and you have minus root 3 here. So you see that all the odd coefficients of root 3, all odd exponents of root 3, they will cancel, right? And what you have is just the even exponents which will get added up, right? It will double. So it's 2 times the first term is NC0 2 power n, and the third term then NC2 2 power n minus 2 root 3 squared, right? So I can just write 3. Similarly NC4 2 power n minus 3 squared, right? All the way like this till the end. Right? What is more important for us is not this part, it's actually just this much, right? So I see that the sum of these two is equal to 2 times something, hence the sum is equal to even, right? The sum of these two expressions is even. Now my first expression is I plus f and my second expression is f dash. Right, so I have I plus f dash is equal to an even number. But from this but I know that f lies between 0 and 1 and f dash lies again between 0 and 1, whereas I, which is an integer, when added with f and f dash, which both of which lie between 0 and 1, in one case f can actually take the value 0, right? So I have I plus f dash equal to another integer. So that means f plus f dash, which lies between 0 and 2, right? It's never equal to 0 because of the inequality of f dash, right? Whereas the right hand sides add up, and I have this inequality, right? Inequality, right? Now, since this is an integer, the only integer f plus f dash can have is 1. So from this I have f plus f dash is equal to 1 actually, right? Now since I plus f is f plus f dash is equal to 1 and the sum is equal to an even number, hence I must be equal to an odd number, right? So the question asks us to find out if I is odd or even, and we now know that I is actually odd. Okay, that part is done. Now we knew that. Now let us look at this condition: 2 plus root 3 power n, which is I plus f, right? The next one is actually f dash, right? 2 minus root 3 power n, but f dash is nothing but f plus f dash is equal to 1. So f dash must be equal to 1 minus f, right? This is equal to 1. So we have solved the question now. So this was actually a very good question, right? You have to first use the fact that 2 plus root 3 into 2 minus root 3 is equal to 1. Also the properties of fraction here, and so we deduce that I is actually odd. At the same time, we will prove the result that I plus f into 1 minus f is equal to 1. Question number 11 here. How many non-prime factors are there in the number n is equal to 2 power 5 into 3 power 7 into 9 squared into 11 power 4 into 13 power 3? Now there is a catch in this question, right? If you look carefully, 9 is not a prime number, right? 9 is just is 3 squared. So I can actually rewrite this as 2 power 5, 3 power 7. There is also 3 squared, right? So that is 3 power 4. So 7 plus 4, that is 11. 11 power 4, 13 cube. So let us just find out the total number of factors first. So total number of factors. There is a very simple formula for that, right? 5 plus 1, that is 6. 11 plus 1, 12. 4 plus 1, 5. 3 plus 1, 4. Right? So all of these will multiply. You have 6 into 5. That's 30 into 4. 30 into 4. That is 120 into 12. That is 1414. Okay? This is total number of factors. But how many prime factors are there? There are only 4 prime factors, right? We have 2, 3, 11 and 13. And these are our prime factors. Hence the total number of non-prime factors is just subtraction of these 4 numbers. So that is 1440 minus 4, 1435. Right? So this is a very simple step which sometimes may confuse you. Now the prime factors actually can only be these 4 numbers, right? Every time you take the next coefficient, that will actually give you some composite number, some term which will be some term which will have this prime number as its factor and hence cannot be prime. Right? So non-prime factors is 140 minus 4 only. Sorry, that is 1436. Right? So these many non-prime factors exist. Find the largest value of n for which 125 factorial is divisible by 6 power n. Okay. We just did this formula at the beginning of this video, right? So what we do here is we first expand 6 power n, right? So 6 power n is nothing but 2 into 3 power n is nothing but 2 power n into 3 power n, right? Now this should be a very simple step to understand. for any number, say 120 factorial. My n is actually 120 factorial. Now 120 factorial will have a lot of will have a lot of prime factors, right? It definitely has 2, definitely has 3, similarly it has 5, 11, 13, 17. Okay. All these prime factors has its all these prime numbers has its factors. And when you write down the exponent of a prime factor, suppose the exponent is alpha, how do you write it? 125 by p plus 125 by p square, right? The greatest function of all this, 125 by p cube, all this way till this finally gives us no more value, right? Now here if you see, if I take the smallest possible prime factor, which actually is 2, you'll get the highest value, right? As you increase the values of p, the corresponding p and p square for different prime factors will increase for a higher p, and hence the exponent will be lesser, right? But for 6 power n2, we to divide 1 factorial, my 3 which will give me a smaller coefficient, that will decide the overall coefficient of 6, right? This is the part which has to be understood in this kind of question, because the formula is pretty straightforward. Just have to understand that 6 power n will be divisible by the highest exponent of its highest factor, right? Which is 3 here. Highest here means the largest factor. So which is 3 here. Who will not decide the exponent? So let us just find out the exponent of p straight away. That is, so n here is 125 by 3 plus 125 by 9, that is 3 squared, right? Similarly 125 by 27, then it is 125 by 81. Next is 125 by 243. If you actually look at this term, 125 by 243 is point something, right? It's less than 1 definitely. The greatest integer function of that will give you 0, right? If you take any other number later on, you'll always get 0, right? So we need not write any term after this. Till here we will be fine, right? Now this is 125 by 3, that is 41 point something. This is just 41. 125 by 9 is 13 point something. Again, just 13. Similarly, 125 by 27 is 4, and this is 1. Right? You have 41 plus 13 plus 4 plus 1, which is equal to 0. So we see that 6 power, not n anymore. We know the value of that. 6 power 59 will divide 125 factorial. 6 power 60 will not divide, and obviously 6 power 58 will divide. Okay, so for this kind of question, you can actually just find the exponent of both 2 and 3, right? And obviously the smaller one will be the one deciding the power of 6, or you can directly move and find the exponent of 3, right? Obviously that will save you much more time. In how many different ways can 3 persons A, B and C having 6, 7 and 8 1 rupee coins respectively donate rupees 10 collectively? Okay. So we know that all of them are somehow donating 10 rupees, and since all of them have only 1 rupee coins, we even know how much money they have got. Okay, so it's A, B and C. So let us just represent the amount donated by A as x1, B as x2 and C as x3. So this is the amount donated by all these 3 persons individually. The condition we have is x1 plus x2 plus x3 must be equal to 10. Right? They donate 10 rupees. So x1 plus x2 plus x3 is equal to 10. Now what we do is, this is the standard problem from multinomial theorem. So we first try to expand it in terms of multinomial theorem, right? Now we know that x1 can be from 0 to 6. Okay, so these inequalities, do it carefully. x2 can take values from 0 to 7. Similarly, x3 can take values from 0 to 8. And the maximum money they can donate is the total number of coins they have, right? So 6, 7 and 8. The minimum is obviously 0. They can't donate negative money, obviously. So here I write that their donation in terms of the exponents. Okay? So 1 actually corresponds to x power 0, right? So suppose, so this is for the first person. Okay, so this is the amount he may donate, right? So that can be 1 or x power 0, x power 1, sorry, plus x square. So suppose I take this term, that means he has donated 2 coins. Okay. Similarly, I write for person B, and then 1 plus x all the way till x power 8. So I look at this expression, and what I understand is the different terms here, when multiplied and when finally I get that huge expression, the different terms are nothing but the total amount donated by these 3 persons collectively. Okay, but I know that they have to donate 10 rupees collectively, right? So the only term I'm interested in is x power 10. Right? So this is the part where this problem actually becomes very interesting. What I need to do here is just consider x power 10 and consider its coefficient. So all I am concerned now is the coefficient of x power 10, and that should give me the total number of different ways in which these 3 persons A, B and C donate 10 rupees. So this is now given by the first one can now be written as 1 minus x power 7 by 1 minus x. Second is 1 minus x power 8 by 1 minus x. Third is 1 minus x power 9 by 1 minus x. Right? Or this is 1 minus x power 7, 1 minus x power 8, 1 minus x power 9 to 1 minus x power minus 3, right? I'll just expand the first 3 terms here. So this actually has a lot of terms, right? But I am interested only in the terms which will be less than 10, right? Because for to find the term having x power 10 when multiplied with this term here, the maximum the terms here can be x power 10, right? So if I take x power 7 and x power 8, x power 50, but here I will have no term which will be less than 1 or x power 0, right? So I can just write this much for this expansion. This will suffice for my question here, right? Now this is again an interesting exponent, interesting binomial expression, right? So I see that this can now be written as 1 plus 3c1 x plus 4c2. So we see that n here actually increases. The n which is usually constant actually here increases. Obviously the r increases by 1 every time. So similarly I get something like say. So for the last one it will be not for the last one, the last we are concerned about. So actually this goes on like this, but we are not interested for anything after this, right? Because we have got x power 10 here. X power 11, 12, 13 all the way till infinity will not be of any use to us. Okay? So we see that the terms we are concerned about here is x power 10, and hence when I multiply this with this term, I get x power 10 here, right? Okay. So the way I get my the coefficient is nothing but so 1 into 2 is 12c2, right? That is 12c2. I have x power 7 here. X power 7 will be multiplied by x power 3. That will give me x power 10, and hence the coefficient corresponding to that is 6c4, right? 5c3 x cube, 5c3, 3. Similarly, for x power 8, I have 4c2, and then I have 3c1. Right? Sorry. All of them are actually with a negative sign here, so I have to subtract all of these last three terms. Solving this will actually give me the different ways they can, and actually this is huge. This is actually 47, right? So there are 47 different ways they can combine to give to donate 10 rupees. Just look at another question for multinomial theorem. In how many ways can we get a sum greater than 17 by throwing 6 dice? Okay, so first we address the problem in. Let the different die be denoted by 1, 2, 3, and hence the number by x1, x2, x3, then x power 6. This must be greater than 17, right? So what we actually consider the case is just the opposite. So instead of 17, we consider the sum to be less than or equal to 17. Okay. So instead of less than or equal to, what we now do is we introduce a dummy variable x7. Okay. So why do we do that? We do it so that the sum becomes 17 now. Okay, so it's you'll appreciate all this in a few while, in a short while. Okay. Now, since the first 6 are the numbers given by so the first 6 are nothing but the numbers given by the die. Hence, they have some restriction, right? So x1, 2, 3, all the way till 6, they can lie between. They have to lie between 1 and 6, right? The ends inclusive. Whereas x7 just needs to be greater than 0. Okay. So again, what we do is we just expand this in terms of the way we expanded the previous question, and consider the term x power 17. So or the coefficient of x power 17. So x power 17 in for the first term we have x till x power 6, but this actually is the same case for all the 6 times, right? So 6 power 6. The last one actually starts from 1, right? So this is my expression here. I have taken x common so that we can actually x power 6 here, x power 5, whereas the next term is nothing but 1 by 1 minus x, or 1 power x minus 1 minus x power minus 1. Now see that there is x power 6 here common for every term, right? So instead of x power 17, I can now just deal with x power 11. Right? I can just divide the whole thing by x power 6. So what I have is x power 11 in 1 plus x till x power 5. Oh sorry, this is power 6 into 1 by x power minus 1. Expanding the first part here, I have 1 minus x power 6 whole power 6 by 1 minus x, right? And that again is raised to power 6. So that multiplies and gives me 1 minus x power minus 7. So I am concerned with x power 11 in this whole thing, right? Now if I expand the first part, I have 1 minus 6c1, that is 6 actually, plus 6c2 x power 12, right? Now I just need x power 11. So actually, I don't even need to expand it beyond the first term. So in the second term here, you should give x power 6. That into 1 minus x power minus 7. Right? So the first term, I have 1 here, and this one will be given by 7 plus 11 minus 1. C. So this actually is nothing but 1 plus 7c1 plus 8c2, sorry, x into x squared, right, like this, right? For x power 11, what do I have? X power 11 is actually 17c11, right? So I have 7 plus 11 minus 1, c11. This is for the for x power 11 from the first term, minus 6 into, it is already x power 6 here, so I am considering the x power 5. It is 11c5. So this is 17c11 minus 16 times 6 times 11c5. Right? But this is my total number of ways in which the sum is less than or equal to 17. Right? So the dummy variable can now be excluded. This is the total number of ways in which my the sum of the sum is less than or equal to 17. So for the sum to be greater than 17, what I have to do is, total number of cases is actually 6 power 6, right? So I'll just grab this by n here instead of s. Total number of ways is 6 power 6. Every die can have 6 different outcomes, and there are 6 power 6 minus this whole thing. Right? This is just the complement of what we are supposed to find out. So we find out the total number of cases for the situation here, and for our case, the favorable outcomes will be given the total cases minus unfavorable outcomes here, and hence n is given by 6 power 6 minus 17c11 minus of 6 times 11c5. The last question here: in how many ways can 3 boys and 2 girls sit together in a row such that between any 2 boys at least 2 girls sit? Okay. Let's say the first boy sits here, V1, then V2 here, V3, right? And let the number of girls sit here be X1, X2, X3, and X4. Okay. So we now need these two to be at least 2, right? Whereas X1 and X4 can be 0. So what we get the condition here is, the first condition obviously that X1 plus X2 plus X3 plus X4 is equal to 3. At the same time, X2 comma X3, both of them are greater than 2, right? Obviously they are less than 15. Similarly, X1 and X4, they actually can be 0 too. So obviously all of them are integers. So what we do here is, we consider the quotient X1 15 in, now let us expand. So X1 and X4, both of them take values from 1. Right? So this squared, and then the next one actually starts from X squared, and that is again squared. Now from here actually I can take X squared common from the second bracket, and that squared will give me X power 4, which I can divide throughout. So I have X power 11. Right. So now I see that I have both the expressions as the same expressions, right? So I can actually write them as power 4, right? So this is actually just equal to the same thing. So 1 plus x squared power 4. Well, that is actually nothing but 1 minus x power minus 4, right? It's 1 by 1 minus x, and the whole thing is power 4. So it's 1 minus x power minus 4. Right? So this is actually, now this is 1 plus 4c1x plus 5c2, so it is 5 not 6. Okay? 5c2x squared, 63x cubed, and so on. Or this can be written as 14c11 for x power 11, right? So I need x power 11. The quotient is 14c11. Right? So this is the number of ways x1 plus x2 plus x3 plus x4 can be taken such that x2 and x3 is greater than or equal to 2, and x1 and x4 greater than or equal to 0. Right? But at the same time, these are actually 15 girls, right? So 15 different girls, obviously, and the boys again are 3 different boys. Right? So the total number of ways in which you can make this kind of sitting is potence 11, and for each such arrangement, the boys can interchange among themselves, and since there are 3 factorial, and each of these individual girls can again permute into 3 factorial ways, right? So you see that the number is actually pretty huge. These are the total number of the ways of sitting those girls between the boys, and then the boys and girls can individually permute 3 factorial into 2 factorial ways, and this gives you the total number of ways. So that concludes our lecture on binomial theorem. We have also covered questions for multi-domain theorem and a bit for prime numbers, numbers and the total number of divisors. So that concludes this video. Stay tuned for the further videos. Thank you.